Hi, so my name is Vichaj Muthumani and my team's paper deals with the topic of do GANs have a Nash equilibrium or not. So GANs are basically a two-player same min-max game that's played between two neural networks. So one of the neural networks it takes the role of generator, and the job of the generator is to take in random noisy input and make fake data out of it. And the second neural network, it takes on the role of discriminator, and the job of the discriminator is to be able to tell apart the real data from the fake data. So now we will have a look at the mathematical expression which is used to represent the GANs as a min-max game. Okay, so here is the formula for the same, the objective function. So what does this objective function actually mean? Okay, so if you look at the term which I have marked in the circle, g of z, that is basically feeding a noisy input z into g, and the job of g is to be able to make fake data. Now g wants to make fake data which is as super duper close to the real data, right? And his incentive is to try to fool d so that d cannot tell the difference between what is real and what is fake. So that's what I've shown in the slide. Job of the generator is to fake data to fool say the discriminator, and now the generator actually wants to reduce the gap say between the fake and say the real data. So that's his job, and that's what he's working towards. So now what's the job of the other player, D, right? His job is to be able to tell apart the difference between what is fake and what is real data. So he wants to maximize the gap. So see the term, he wants to maximize. So while the other guy wants to reduce or make min, so this guy wants to max. So hence it's a min-max game, but we'll get to that. So this diagram is diagrammatically showing what was explained in the last slide. Look at the generator. What he's trying to do is to reduce the gap say between the fake data, the real data's distribution, and the other chap, right, discriminator, he's trying to maximize the gap. And so this interaction, right, of the min and the max is what makes it into a min-max game. So here the paper's authors, they use the min-max objective function, and the min-max objective function basically gives the divergence between the real data and say the fake data, and they wanted to see if the divergence would go down to 0. If the divergence was to go down to 0, so that means that the standard GAN that we used to train to make the fake data, it actually matches the real data distribution exactly. But from the experiments, it can be seen from the picture that that's not the case. So you see the blue line, right, that represents the divergence. It starts to drop. After a point, it no longer drops, and it never truly reaches 0, based on the experiments done by the authors. So they came to the conclusion that a standard GAN is not able to reproduce the exact data distribution. The paper's authors came to the conclusion that we were dealing with a non-realizable setting. So now under this non-realizable setting, they wanted to know if wherever we end up after training is a local Nash equilibrium. So to answer that question, so what the authors did was they fixed D and they just optimized over G. So G is the fake data generator, right? So when they did that optimization, they found out that the min-max objective, actually started to fall down. So it actually started to decrease, and moreover on top of that, they also saw that the fake numbers that you get from the generator, they started to look worse and worse. This showed the authors that it was not a Nash equilibrium. If it was a Nash equilibrium, right, when we try to do optimization, there would be no incentive for G, player G to change. But player G is clearly changing. So this shows that we are not in a Nash equilibrium after training. So this finally leads us to the motivation for this paper. And the paper's authors, they wanted to define a notion for a GANs equilibrium. They go about doing this by a technique called as proximal training, and my teammates will be explaining more about that and all the mathematical integrity, and we'll also have a demo of results from a training of proximal GANs at the end of the presentation.
I will talk about what is the proximal equilibria. Proximal equilibria is a spectrum between the Nash and the Stekeberg equilibria. The Stekeberg equilibrium of the GAN game can be described by these functions, and the lambda proximal equilibria can be described like this. You may have a question why we need the proximal equilibria. Yes, you know that Nash equilibria will not always exist in the GAN game, and however is very stable. Stekeberg equilibria can be promised to exist in GAN game, but it's not very stable. So the proximal equilibria is needed, and it can help us to increase the result of the GAN. Okay, let's talk about the proximal equilibria in WGAN. The WGAN minimized problem can be generated like this, and a Sobolev semi-norm averaged over the underlying description of the data. Px is to define the proximal operator of the WGAN. We consider a parameter set of the generator G. This theta is defined to be the optimal discriminator function of the parameterized generator G theta. This theta provide the Bernoulli theorem. We can get these equations, minimizing a strongly convex function over convex set implies these functions, and this function will help us to build the model or the network of the GAN. Yes, in this project we repeat the work in the paper, and the code is available on GitHub, and you can find it on this website. And we choose the model WGAN and over the CISAR10 dataset. This optimizer was used in our experiment. In our experiment, we should first train the networks. Then we will have a trained then we'll have a trained discriminators T, and we'll fix this to optimize to do the proximal trainings. We optimize the proximal object with a lambda equal to 0.1 to solve this problem. And this is the date of our this is the date during the training of the network. Yeah, this is the result of epoch 1, and this is the result of epoch 200, and we can't find any difference between the epoch 200 and the epoch 100 based on our eyes, but based on the loss state, the loss of the epoch 200 is much smaller than the 100. And this is the date during the proximal training. And the process is too slow, so I can only run the iteration for about 150 times, and this cost me about 2 days. It's a very slow progress. Yes, but based on the loss state, we can make sure that the proximal training will help us to get a better result. Yes. The conclusion of us is that the result of us are very similar to the paper. Yes, you can find, and yes, based on the loss state, it's same in these pictures. And we observe a somewhat improved quantity achieved by the proximal training. And yes, based on our loss state. Yes, the proximal training will also cost a lot of time. And it's much longer than the normal training. Okay. And this is also same to the description in the papers. Yes, the last part is our reference. Yes, thank you.